This is our project on exoplanets and obliquities. I'm Troy Taman.
I'm Lucas Kittle.
And I'm Maria Carpet.
And we work under the mentorship of Dr. Aurora Kesseli of IPEC.
All right, so we'll start with some background. What is an exoplanet? So an exoplanet is just any planet that orbits any star that is not our own. And oftentimes these planets are very different from our own system. For example, this is the orbit path of a star TIC 24124953OB. And as you can see, it is on a highly elliptical orbit. So this is a Jupiter-sized planet orbiting closer to Mercury. And it just really puts our system into perspective.
So we focus on the obliquity of planets, and the obliquity is the angle between a planet's orbital axis and its host star's rotational axis. And if you have an obliquity closer to 0 degrees, it's more aligned with the host star's rotational axis, whereas an obliquity closer to 180 is misaligned. So for example, the solar system is aligned because all the planets have an obliquity of less than 10 degrees.
So there are two types of obliquities, a projected obliquity and a true obliquity. Projected obliquities are 2D and represent the measured angle between a planet's orbit and the star's rotation axis based on our perspective from Earth. It's calculated using the Rosser-McLaughlin effect, which is caused when a planet rotates around the star and blocks some of the blue shifted and red shifted light of the star. Because the starlight from the star is shifted in our line of sight, this is the true projected effect. The true obliquity, on the other hand, is 3D and measures the actual angle between a planet's orbit and star's rotational axis. True obliquities are more complicated and they require information about a star's rotational period, stellar inclination, and other parameters. But they're important because if we understand true obliquities, we could possibly understand how exoplanetary systems outside of our own form.
Yeah. So building off of that, why are obliquities important? So like Sharia just said, they can really just help us learn more about the formation of these systems. For example, the planet that I showed earlier, the true obliquity can really help us understand how it may have gotten there and really just understand more about every other exoplanet system. And that leads into the goals of this project. So we want to, first and foremost, increase the number of true obliquity measurements that we have for just all exoplanets, because right now there are less than 60 total true obliquity measurements for the almost 6,000 exoplanets that we've discovered. And we do this via several methods, which we'll get into later. All right, so where do we get our data? So this is the NASA Exoplanet Archive. It is created and ran by NASA and JPL Caltech, and it includes every single data point for every single exoplanet paper published. And this is very, very useful for our calculations of true obliquity.
To calculate a true obliquity from a projected obliquity, one thing we need is a stellar rotation period. This is the time it takes for a star to complete one rotation around its axis. Stars have star spots that appear on their surface, and as the star rotates, these star spots rotate into and out of our view. This causes the star's brightness to vary, and we can measure this change in the brightness to calculate the rotation period of the star. For instance, our sun has a stellar rotation period of 25 days. To calculate the stellar rotation period, we need a lot of data, so we use the publicly available TESS data. TESS stands for Transient Exoplanet Survey Satellite, and it was a NASA mission launched in 2018 to find exoplanets. TESS basically stares at one area for 27 days, which is called a sector, and it takes precise data of the changing brightness of stars across that entire sector. We access this data using a Python package called LightCurve. So here's a star called TOI 1136. And I downloaded the test data available for it using LightCurve, the Python package, and then I made a light curve out of the data available. The light curve measures the brightness in the vertical axis and the time in the horizontal axis. And these light curves are useful to astronomers to calculate things such as the planet orbital period and the stellar rotation period, which we're calculating right now. Most of the stars that we observe have a planet orbiting around. And when the planet blocks some of the starlight, this creates a transit dip. These transit dips are shown in red. And these transitives don't reflect the stellar rotation period that well. So we delete these points from our data so that they don't mess up our calculations. How we delete this is we make a transit mass out of the planetary parameters that's found on the NASA exoplanet archive. From here, we do what's called a Fourier transform, which basically fits sine waves of varying frequency on the light curves and outputs a periodogram. The periodogram tells us what period matches the light curve the best. So the peak of the periodogram represents the stellar rotation period. We got a peak at 8.6 days for this star, which matches the published value of 8.7 days, according to a paper in 2022 published by Dye and others. Here's another star called XO6. However, you can see that the data is very noisy for the star. This can mess up our calculation of the rotation period. However, there's another technique called stitching, in which we combine multiple sectors of data for the star to make one large light curve, as if you're stitching multiple small light curves together. This gives us more data to work with, which could increase our accuracy of calculating the stellar rotation period. Then we do the Fourier transform again, and we get the peak, which gives us the stellar rotation period. The Fourier transform is primarily useful for stars which have a lot of data and stars which could have a longer period, as this test satellite only observed each sector for 27 days. However, we still got really good results for this star. We calculated the stellar rotation period of 1.8 days, and this was a result that no other paper has ever reported before.
To calculate true obliquity, we first needed the rotational period of the star, and we use that to calculate the stellar equatorial rotation velocity. And using this value, we also use the projected stellar rotation velocity to get stellar inclination, which tells us the angle between the observer's line of sight and the star's rotational axis. And then we use stellar inclination as well as the planet's orbital inclination and projected obliquity to finally get true. And so for my part of the project, without calculating anything, I went through the exoplanet archive and tried to find planets that have measured values that we need to calculate true obliquity, but no actual confirmed or calculated true obliquity yet, to try and fill in the data and for true obliquity starting now. So I found 31 planets with enough information to do so. And there were a lot of instances where there wasn't a single paper that had each and every measurement. So by mixing around the different values from different papers, we managed to increase the original amount of true obliquities by 56%.
And then we also found 22 planets that had everything necessary except for the stellar rotation period. And so across those 20 stars, we found those stellar rotation periods and used that data to calculate the true obliquities.
Okay, so we plotted the true obliquities we calculated as well as their respective projected obliquities. And at the top, we did these values for planet mass, and we did not find any clear trends, which could imply that the process through which these planets got to be where they are and how they align does not necessarily rely on their mass. But on the bottom, we found a stronger positive correlation between our calculated values and stellar effective temperature, which matches the fact that cooler stars have a bigger convective zone through which they release their heat. So the heat comes out in the form of physical gas, which creates motion and kind of aligns the planets around it. But as stars get hotter, this convective zone thins out, and there's not as much physical gas to align the planets, which is why the obliquity gets greater.
All right, so this final graph summarizes all of the true obliquity calculations that we've done. So the ones that Maria has found are shown in blue, while the ones with stellar rotation period, the ones that we found in Sharia are shown in red. And as you can see, there is again that positive trend that Maria explained. So hopefully in the future, we can add more points on this graph and continue our research.
Thank you everyone for listening to our presentation. We would like to give a special shout out to our mentor, Dr. Aurora Kesseli, for all of her guidance throughout this 6 weeks, as well as all of IPAC for their assistance and hospitality. We would also like to thank Nick Tuesday for using one of the animations from the earlier slide, for letting us use it. And we'd also like to give a shout out to Mr. Mitch Eichen and Dr. Katie Kalen for setting up the Summer Research Connections and giving us this amazing opportunity to do some research. Does anyone have any questions? Yes?
So how confident are you that the peaks in luminosity are due solely to star spots moving opposed to other, are there other phenomena that could cause those peaks other than just star spots? Yeah.
For most of these stars, we are pretty confident that these are just other rotations. There are some stars where there's like a specific boundary where the stars start oscillating back and forth, which is pretty interesting. So those stars we're not confident about, but there's like maybe 2 or 3 of those stars. But for most of these stars, we're pretty confident that these are the stellar rotations. Any other questions? Thank you.